Hello, everybody. Welcome to this new CivilFEM webinar. Thank you for attending. Today, we will explain some utilities or some dynamic features. As in this case, will be about transient analysis using CivilFEM powered by Mark 2018 version. I'm Ronald Siat, and I'm very glad to be your lecturer today. So, usually, in this kind of this powerful software, you always can go beyond static analysis. Sometimes our structures will be subjected to certain loads which are not static, which instead they are can be variable in time. The loads can be point loads, pressures, it can be displacements, accelerations, can be if we go to a thermal analysis, can be temperatures or material properties, variable in time. In seepage analysis, it can be a flow, pore water pressure, water tables, okay? And always this phenomenon is more complex if we take into account nonlinearities as large displacements, material nonlinearities as plasticity, any other nonlinear strain stress material contacts. Okay, we can always include nonlinearities, so the convergence will be more difficult to achieve, but you will see that in CivilFEM the analysis for advanced, in this case, for the advanced dynamic analysis, very easy, and most of all, you will always obtain accurate results. This technique is very commonly used under actions such as impacts, impulsive loadings, seismic actions, explosions, thermal loads in transient state, mechanisms, vibrations, and as I said before, analysis of seepage in transient flow conditions. Okay. First of all, we want to start from some fundamentals, from basics, to show you how to perform easily and fast and transient analysis using this cantilever beam example. This exercise is just a beam element subjected to a force which will be deleted, will be applied suddenly, and in I think it's only 0.02 seconds. Impulsive force, it's still a steel beam, and the force is 500 pounds. Okay. One of the important things of an transient analysis is to decide which will be the size of the time step. The size for the time step, or in the step fraction, is always governed by the maximum mode frequency of the structure. The preferred minimum number always is for the step fraction is 10, between 10 to 20. Of course, 20 is better. Steps per period. In order to obtain frequency and periods, we have to perform a modal analysis to determine the modal shapes. We will see how to perform this easily in CivilFEM. Okay. Of course, the smaller the time step, the higher the mode frequency we will capture. But and sometimes if we set a very large time step, we won't get, or we won't capture accurately the amplitude of the response of a structure. So that's why we recommend always to set this rule of thumb, which is between 10-20 steps per period. Okay. What else? In CivilFEM, powered by Mark, we can include, of course, damping. So we can see which will be the influence of damping, including analyzing a damped solution or undamped solution. How can we define the damping value in CivilFEM? In many ways. We will see how to apply transient load in CivilFEM and how to post-process transient results in CivilFEM. Okay, if you already accustomed to this graphical user interface, it will be very easy. But if it's your first time, you will get it very fast as well. This is our beam. I used a Python script for this example. Okay, it's very easy. Just I set my analysis, my name, my units. I set my line. I define my steel material, my cross section. Maybe with an editor you can see better, and I define my boundary condition, which is fixed at one end, and I will apply a load variable in time, a transient load, a tip load. Okay, but first of all, important thing is material. By default, damping is not included. Damping will be present in all oscillatory systems, and well, the value of damping will dissipate the energy of my system. Okay, and in a free vibration, the effect will give a decay in amplitude, or in a steady state will give energy loss. Okay, there are many damping types, and structural, viscous, modal, Rayleigh damping, and we will see how to define damping in Civil. How you see here, there's these coefficients. We can Rayleigh damping will be proportional to either the mass and the stiffness matrix. So the alpha damping, the mass damping coefficient, is this, and the beta damping, which is the structure or stiffness damping coefficient, can be set here. Okay, or you can, and as well, there's another way. If you want to set a percentage of the critical damping value, you can set it here using these values as well of the minimum and maximum frequencies. It can be automatically calculated the Rayleigh coefficients. Okay, by default we will set an undamped solution. But first of all, as I told you before, we can obtain a modal solution. To obtain a modal solution, just go to solve and configure a different way of extraction of modes, which by frequency range, a minimum and maximum frequency, or number of modes. If I want to set 10, I can solve, and I later have my results. My 10 results are here, and I can obtain my information. For each mode, my frequencies, periods, and participation factors. The first one, you can see that the it participates mostly in Y displace in Y axis. And my second mode, which will be the one we will consider, is the one participating in the Z axis. We can see it here if we plot the former shape. This one participates in the Y direction, and next one it's in the Z. Okay. We here see the table. So it's the previous one. Here we can see this value of frequency and our period, which will be taken into account to determine the time step. Okay. So first of all is the modal analysis. Now we can turn to a transient analysis. Okay. Once we are in the transient analysis, our loads will be time dependent. Here it is, my load, a load applied here, but now I have to assign my values according to a timetable. I can delete rows or I can include them. I set this time. My force of 500 pounds will be applied until 0.02 seconds, and then it will be dramatically deleted until the end of my analysis. Okay. And then I just set my boundary condition. I can include an initial condition if I want, and I solve my, well, will be my, in this case, undamped solution. If one of the, as we told you, one of the, I will set important things is to set these fractions. If I want to divide and set my own value to divide my analysis into 10, divide my total duration time in 10 steps, I will set here the step fraction, which is 0.1. My total time is 0.02, so I will, if I solve, I will get undamp. I will solve here. I turn out the output so we can check here. Here we can see that I have defined for the transient undamped so I want to, as I will delete first all, as I have results from a previous analysis, I will delete all of them first, so I won't have any conflict, and I will solve again, because using different time step will create a different number of results. Each step will be stored in a different result file. In this case, I have defined 10 files. I can get the information. As you can see, each step is 0.002 seconds, a total of 0.02 seconds. But if I want to plot results, this history plot is the way of plotting results, transient results in CivilFEM. Of course, you can plot one by one using the standard plotting, but here we can plot any value versus time or versus other values against reactions or other results. But here I want to plot my vertical displacement of some nodes. For example, this one, my 10 last nodes. Okay. If I want to plot my displacement according versus time, I can see here that the capture of the frequency is not very accurate. You can see these graphs, these charts says that at 0.004 seconds we have a displacement of minus 0.11 inches, but it's not very precise because we didn't set a correct value for the time step. So what is the value that we recommend? As I told you before, here this is the Python script. Here we can we know the frequency, so therefore we know the period. At minimum, we need 10 steps per period, so we divide it by 10, and we divide it by the total duration of my calculation time. So if we set this value here, CivilFEM can accept a formula, and as well we can set a parameter as well. Then now I can solve again. This is the undamped. Sorry. I said an incorrect name, but it's no problem. And now we'll see that more result files will be created, and we will check again the results. So I told you we can use the standard plot here. You see here, and now I have to select my new files, the undamped solution here. I can set it undamped, and I will plot now a new chart. And now we can see that result is more accurate. You can see here eight cycles. We have solved 8 cycles, and our static solution will go here just in the middle, around 0.7 minus 0.08 inches, and a maximum displacement of almost 0.15 inches, but using a undamped solution. If we want to take into account damping, then we can set here a value and see how the energy will dissipate. Set here, and to change, to not overwrite the previous solution, and we can start again the analysis of this simple example. As you can see here, we have eight cycles, as we have defined these time time step properties. As we have performed first a modal analysis, now we will have transient results using our history plot. I will wait until my results are obtained. Now if I go back to my history plot, now I have to select again now my dump solution. If sometimes the results are not correctly in order on time, this button can be sorted. Okay, if I plot now my dump solution, we will see how now dumping is taken into account, and we see that at the end the movements are almost zero. Okay, so this is just a simple example just to show you how to in a easy way how to use dumping, how to define a transient loading, and how to post-process results in CivilFEM. Now we can see more other complex examples. Okay, we have seen this. Now we have this steel structure, a steel cabin, and we applied as well an impulsive pressure. In this case, it's a pressure 90 kilopascals in 0.2 seconds, applied in X direction and in Y direction. And we have activated as well the bilinear constitutive law for the steel material, so we can include plasticity and check. The model is this one we have here. Okay, we have this, or geometry is this one, and we use beam and plates, beam and shell elements. This structure has reinforcement in Y direction. Okay, if I run out if I hide some elements, you can see, and we apply, here we go, explosion in Y and in X direction. If I to set this explosion, I just define some pressures applied to our structural elements, and always using a table. I set my different columns. First, my time column and my force column. Okay, so my chart, this is my loading, 90 kilopascals, and then will decrease dramatically to zero until the end of the analysis, 0.18 until 0.2. If I plot my force image, this is in X direction and in Y direction as well. Well, here we presume that the worst results will be in this direction, as in the other direction the structure is reinforced with these beams. Okay, we can solve using explosion in X and Y. I have just solved for X, but we can solve both and then create an envelope. And here we can see some video animation that can be, of course, in CivilFEM you can animate and create your own videos. Here we plot the component of the X displacement, and you can see that the rebound and how this explosion affects as well the roof and other panels and other walls. And here is the von Mises stress result to check if the limit stress is reached. So some elements are yielded. Okay. We can, of course, use again our history plot. We can always or obtain plot our result one by one. Okay, here you can see using this our standard and of course any result can be plotted. Okay, or we can again plot the results. We can plot the displacement in X for some nodes just located in the front and lateral, and another at the back. For example, the one at the back you can see here, which is the movement, the X displacement of that node, which will amplify, and the ones at the front. This is the one at the front. It has a peak at 0.02 seconds, and then, as you remember, the explosion was suddenly deleted until 0.2, and this is another node of the front, and this one of the lateral. Of course, you can always set values for damping. In this case, they are not used, but you will obtain different results. Okay? So we have seen how to define a point load in a beam, pressure as well, a pressure loading, all of them transient loads. Another way of defining a transient load is, in this case, not an impulsive force, but a moving load on a box. In this case, it's a train loading on a box bridge. In this case, the behavior of the load is not the same as the rest of the forces we've seen before, which is just a peak force and then deleted at certain time. In this case, the load transition is smoother, but we will have to, the load history must be defined in this as it's shown here. The moving load will be present all the time, and the load quantity needs to be constant for each time. In this case, we will. This bridge has been presented in a past webinar. It's pre-stressed box bridge with a construction phase, but well, this is not the case. Today we will study the moving load of a train with 12 cars along the bridge. This bridge has 92 meters of length, and we'll see that we have defined 12 train AVE cars, which will be moved along the bridge. Each load per axis load of each car are between 131 kilonewtons to 172 kilonewtons. We define a speed of 225 kilometers per hour and a total of 4.3 seconds of calculation time. So we will get all the 12 cars starting from the beginning with the first car, then the second car will appear, the third, and with taking into account the separation of each axis, we can set the spacing in time, because we have to we'll set different timing for each car of the 12 ones. So to define that, we can do it, of course, always manually. This is our bridge. Okay, it's a bridge which is a slab, diaphragms, it's piers, and as I told you before, it's stressed, and now we have included a moving load. These are the tendons. Okay, I will put them again, and now I want to apply a moving load. How to define a moving load? Well, besides other loads that the spectra, pre-stressing, heavy traffic, and other loads, the interesting one is how to define a moving load. If we click here, as you can see, we have defined 12 of them. We have to set the name of the load, set where is located the structural element. In this case, the right, it will be applied only on a right lane. Of course, the codes always recommend us different loading scenario, but in this case, we just set in so we can see the asymmetric results. The direction, in this case, is following the x direction, and the path. The path we have is just a line that will be created to be followed. And then the initial time for the first moving load will be 0. For the second one will be another value, and for the third one, fourth one, depending on the separation between the head of the first car and the following one. The speed, which is constant, the 225 kilometers per hour, or it's about 64 meters per second, and the number of steps. This is the number of times that the moving load will be applied depending on the accuracy that we want in the model. In this case, we set that 25 steps will define 26 point loads here, as you can see. Okay, the same, and if we once we define this moving load, automatically all these point loads will be defined following. These are automatically created. And these tables are automatically created, the table of times and table of forces. And the same for other depending on the car, we have defined, as you can see, different loadings. But always what we want is to follow this procedure. But in this case, CivilFEM defines this loading automatically. Okay, so we just include this load into my this one here into my load case. I set my calculation time. Of course, always set my fraction, which will be 100 times. It will divide my 4.3 seconds into 100. I set the same fraction for its initial minimum and maximum, and I have my results. And of course, as always, what we can do is make use of the history plot. If we select, for example, some nodes on the middle of its span, of course, we can always plot any result by our standard result plots. Here it is. I want to clear my. If I want to obtain the envelope of the maximum or minimum values from all my results, which are all the results. Okay, I have generated all the results. I can create my envelopes. So at the end, I have created the minimum and maximum values. In this case, I can get, here you can see, the maximum, or in this case, the minimum values, which are negative. Minimum deflection from all my transient analysis, which is 3 minus in millimeters, more than 3 millimeters. Other way to plot results is by checking my history results. If I plot them, I can get the results for this. Is the node of middle of the first span at 0.4 seconds. It has a deflection of almost 3 millimeters. Then the node of in the middle of the center of second span it has a maximum deflection at almost 1 second of more than 2 millimeters. And here for the last, the third node, which is located in the middle of my it's around here, this location, at more than 2 seconds, it has almost 3 millimeters of deflection. And of course, we can study more in detail, more nodes, more other type of results, forces, moments, stresses, a long time. It's with this history plot. Okay, and as well, we can always animate the solution. And here's the deflection of after the moving load of my 12 train cars until the end of my analysis, which more than 4 seconds. Okay. Another way of defining transient loads is by is to take into account seismic actions to take for time inelastic time history, for example, or to include accelerograms or any other tables. For example, displacement versus time loading. This masonry bridge has at his foundation, 3 foundations displacement, but this displacement, we have seen that we can define loads versus time, but of course we can set force displacement as well in a transient analysis. We can have a table, a list from a spreadsheet file. We have our column of time in seconds. It's a total of 40 seconds. And these are displacements. If I plot it, here we have my 40 seconds and my displacements, and they will be applied either to one foundation, the central one, the left and right, according to this view. And of course, we have included a nonlinearity, which is cracking of the material. Okay. We have as well a video to see how the cracks are performed during the analysis. Of course, always we can define a load, or in this case a displacement for 40 seconds, but in the solution, in the calculation time can be different, can be less or of that, and always take into account the step fraction. Okay. Another way of taking transient loadings into consideration in CivilFEM, another example are if we are performing thermal analysis. In this case, we can always, of course, include nonlinearities. Here, this is a mass concrete block, and because of the effect of the heat generation from the hydration of the cement, we can see the temperature and stress distribution along time, in this case, along days. You can see different part of the model, which will be and if we want to take into account a water cooling pipe system, we can see if the temperature can be decreased inside the blocks. Always, it's in thermal analysis we can of course always set variables which depend on temperature, conductivity, and other material properties, and as well always in a transient analysis. Another type of thermal analysis very typical is in thermal cracks on a concrete arc dam to include seasonal temperature variations in, for example, summer and winter temperatures can be placed in upstream or downstream. These temperatures, which in a cycle of 2 years, for summer and for winter, this will give us a crack pattern, so we can check the safety of the dam. We have results as the displacement of some parts of the dam. In my history results, as we have seen before, and results, in this case, crackings. If we perform a seepage analysis, transient as well is very important to take into account, and always we can set different conditions. We have seen this in a previous seepage webinar, but just to show you that if we want, in this case, a crack is, we studied the water flow through a crack that's a kind of leak in this part. So we see the pore water pressure distribution along time. And another example is the slope instability under heavy rain, which in this case, according to the strength reduction method, and the nonlinearity of the material, we have studied the collapse of this slope because I think we set more Coulomb as material model in this example. So, well, as you can see, we have many ways of studying transient loading in CivilFEM, any type of load for any type of analysis, structural or thermal, and seepage, always and couple analysis. The way of sharing our expertise is by, well, some courses. If we want a course eminent only for practicing with the software, we have this International Online CEA Education Center, and we have many as well. We have many other courses. If you visit this website, you have more information. And as well, if you want more to include theory or fundamentals to your studies, of course, we have we begin now our 25th edition, and you're always invited to enroll and visit this website. So, well, always you can download a free version of CivilFEM at this site. For more information, you have the info and support account or social media. And if you visit our website, you can always well, take part of our community, which is here. So for free, you can enroll to your community, so you can get a database of examples, share your thoughts, your doubts, ask questions, and here many ways of discovering our software. So thank you very much for your attention. See you in next webinar.